is a first-aid delivery drone that actively explores unknown environments to find survivors and delivers payloads to them. RO provides an efficient payload delivery mechanism, a probabilistic 2D mapping system for thinking about uncertainties in the environment, and a planner for computing safe and optimal viewpoints for finding more survivors, alongside feasible paths to reach them. Search and rescue in post-earthquake zones can be difficult and lengthy. Collapsed indoor environments are often riddled with obstacles and debris, which barricade ground teams attempting to reach survivors in need of time-critical first aid and necessities. A small and nimble drone can quickly find survivors and provide life-saving necessities before ground teams reach them. While existing drones can be piloted to scout for survivors, qualified drone pilot rescuers who know where to look are often scarce. Whether you are a government agency aiming to bolster your disaster and emergency response team, fire and rescue department looking to modernize and improve your response effort, or a non-profit humanitarian organization like the Red Cross, RO's intelligent autonomous exploration and first aid package delivery can be the solution to find survivors quickly and save more lives.
An Intel Realsense tracking camera is used for visual odometry, providing a post estimate of the drone as well as images for APRO tag detection. Tags are mapped as obstacles or targets and added to the occupancy grid. The APRO tags represent a proxy for the perception system. In future iterations, we plan on adding false simultaneous localization and mapping, as well as survivor detection from an RGBT stereo camera. If a survivor is found, the exploration planner will immediately set the survivor's location as a subgoal. Otherwise, the exploration planner will compute the optimal next best view for finding more survivors. Given a subgoal, the path planner will compute a feasible path based on the occupancy grid. The path is then tracked using a position-based controller on board the CubePilot Orange plus autopilot. Upon reaching a survivor, an Arduino Nano triggers a servo motor to drop first aid packages. To obtain a stronger understanding of the search and rescue environment, RO also provides a 3D reconstruction of the environment whenever it's connected to the remote control center. Using the RGB image feed from the monocular camera, a recording of the trajectory can be relayed to the remote server from which a nerf of the environment can be constructed. APRO tags are fiducial markers with unique IDs that has a fixed size. By perspective warping the Realsense images, we can generate the pose of the obstacles and targets relative to the drone and transform it back to global frame from the Realsense pose estimate. This allows us to build the occupancy map with the points of interests. Tags marked as survivors are represented by the green X on the grid. Tags representing obstacles are added as red pillars with a safety radius.
We initialize a map with complete uncertainty, represented as black. Once the drone has stopped moving, we update the occupancy grid and run raycasting from that drone position. In a range corresponding to the field of view of the drone's camera, cells that are close to the drone are marked as free with complete certainty, represented by white grid cells. As rays move further away from the drone, we mark them as free with less certainty, represented by the gradient from white to black in the grid. While many drones can provide perception and mapping capabilities, RO is unique in that it has an intelligent and fully autonomous planning agent that can identify uncertain areas of the environment and explore them, helping find more survivors. The planning module consists of a high-level exploration planner, which provides subgoals to the low-level path planner. RO follows a sequential sense, plan, act loop. After updating the occupancy map from perception, we check if any survivors are found. If there are survivors, we set the subgoal to the survivor pose and ask for path planning towards the subgoal. If no survivors are found, we randomly sample thousands of safe poses from the occupancy grid, defined as cells in which we are above a certain probability threshold of knowing that it is free. Then we calculate the view entropy for each candidate pose. This involves using the raycasting algorithm again, in which we look at the probability of cells being free for each cell intersected by a ray. We then set the next best view as the view with the highest entropy, since going to that pose will reduce the drone's uncertainty over the map the most. The path planner is again queried to find an obstacle-free route to the next best view. Once it is reached, we look for tags and update the occupancy map again. RO begins planning by sampling from a Gaussian distribution around the current pose for some radius r. For a candidate pose PI, it simulates 200 rays from the drone over its field of view cone, given by the camera's intrinsics. Each ray will pass through a set of cells C before hitting an obstacle or dissipating. RO can then compute the next best view for exploring the environment and finding more survivors by calculating the Shannon or information entropy. This value quantifies the average amount of uncertainty or information associated with a random variable. In our occupancy map, each cell represents the variable. A low entropy means that the occupancy state is certain, that is, either occupied or free. We can see this in the bright white cells or the red obstacles. A high entropy, on the other hand, means that the occupancy state is uncertain. This is represented by near black values. Then, the expected information gain from visiting a particular viewpoint is given by summing over the entropy of every cell visible at that view. Rho will then set the candidate pose PI with the maximum entropy as its next subgoal, as that will lead to the greatest expected reduction in uncertainty over the map, meaning it's the best place to look for more survivors. Given a subgoal, whether a next best view or survivor location, Rho will use A* to plan an optimal path towards it.
Rho features rugged landing gear, aimed at improving robustness in the face of rapid, unscheduled landings. At the heart of Rho is the automated payload delivery mechanism, designed for precision delivery of spherical first response modules. The current configuration supports 8 such payloads, but can be expanded. The payload delivery mechanism, as well as the rest of the superstructure, are optimized to minimize weight and downwash interference while providing the required structural integrity.
We rely on NERF, neural radiance fields, which leverages a deep neural network to learn a continuous volumetric radiant field, allowing for the generation of photorealistic views from novel waypoint for environment reconstruction. We begin with RGB images captured by a binocular camera on the drone. These images are processed using CalMap to estimate camera poses. After that, the output is then used in NERF to generate a detailed, high-quality 3D model of the environment. The 3D map can provide rescue team with current situations to allow them to remotely explore the environment and understand the mission in great detail before taking actual rescue. This is especially valuable in these dangerous environments without clear sights.
Here is a video of Rho performing a complete flight in which the slanted tags on the ground represent survivors and the pillars represent obstacles. Rho proceeds towards the first survivor and positions itself based on the next best view orientation. To quantitatively evaluate Rho's performance, we developed assessment metrics, the first of which is Rho's package drop accuracy. Rho should deliver its package within a virtual bounding box. The closer to the center, the better. Afterwards, Rho cannot see any more survivors, so the onboard planner computes the next best view. The second evaluation metric is the next best view calculation speed. We track Rho's time spent at each subgoal and ensure it idles for less than 8 seconds per goal to achieve a balance between a responsive and effective flight pattern. As Rho moves from each subgoal, we observe the occupancy map populating with the new view on the top right of the screen. The final criterion, complete area mapping, stipulates that Rho must explore a minimum of 85% of the map before terminating its mission, with greater area coverage desirable. As part of constraints on the operation, Rho must find all survivors and avoid all obstacles. At this point, Rho observes the second survivor and immediately delivers the package, completing its occupancy map concurrently.
Why use Rho? Rho has perception capability to autonomously map and find survivors as well as provide reliable localization in GPS-denied indoor environment using visual odometry. Rho is also uniquely capable of active exploration, intelligently exploring unknown environments using high-level planner that calculates next best view using information gain. It is able to effectively and safely navigate with A* path planning algorithm, guaranteeing safe and optimal route to detected survivors while effectively avoiding obstacles in the environment. In addition, the servo-based payload dropper allows for precise, software-controlled deliveries while the drone hovers, removing the need to land and thereby reducing the potential risks. Lastly, to help ground team coordinate, we provide a package that converts Rho flight videos into accurate 3D reconstruction of the environment using NERF to deliver key situation awareness. However, there are still several key limitations in both perception and planning. On the perception side, APRO tags offer reliable detections but are not feasible for real-world development. Additionally, our system lacks real-time detection of obstacles and targets. It only processes the environment when the drone is stationary at a subgoal. We also rely on a 2D occupancy grid with a fixed Z height assumption, which oversimplifies even in indoor environment. In terms of planning limitation, the system doesn't perform global path optimization when multiple survivors are detected. It also fails to account for the travel and distance costs when computing the next best view, which limits the efficiency of our searching strategy.
Thanks for listening. This is RO by the ROBROS.